of something using integration. So first off, remember, if we wanted to find the area under just this function, where this is f of x, we would integrate from a to b of f of x dx. And if the curve fell underneath, when we integrated, we would get a negative number. So to find this area, we would have to say negative the integral from a to b of f of x dx. So what if we have two functions? What if we have, here's f of x, and let's say that's g of x. Well, if I integrate f of x from a to b, I will get, let's see if I can do this with a light colored pen. Oh, I thought that was pink. Oh well. I will get that area. Now, if I negate, say negative the area from a to b of g of x dx, that gives me this area negated, and it gives me this area, and it's positive, because since g of x is negative, if I integrate here, I'll get a negative number, so I stick a negative in front of it to make it positive. So effectively, all I really need to do, I don't need to worry about where it crosses the x-axis. The area is going to be the integral from a to b of f of x minus g of x dx. And when we're doing these, I mentally try to think of what is, looking for another pen, what is, I'm going to pick a generic x in the middle. Keep in mind this x is supposed to stand for everything between a and b. If I cut it here, there's my little rectangle there. Now the area of the rectangle is approximately f of x, because that gives me the height. Oh, I should do this one too. Ah, shit. Minus g of x. And then the width here, oh, you can't see any of that. And the width here is represented by our standard delta x. And so we're going to take the derivative, to take the integral, we find the limit as delta x goes to 0, so this gets really, really small. The delta x becomes a dx. F of x minus g of x goes here, and that's why the area works. But so I tend to think of it as, I know the delta x is going to stand for the width, so all I really need to do is think about what is the height of this slice going to be. So let's do an example. Suppose we want to find the area bounded by y equals x squared and y equals 2x minus x squared. So drawing this, x squared looks something like that. This means the parabola is facing down. It's going to go through 2 and 0. So there's my picture. I'm not going to use the graph as any kind of indication of where I'm really supposed to be, because my graph probably sucks. So what I'm going to do is I'll do my little generic slice here, and I'll call this x. I need to figure out where this other point of intersection is. So I'm going to set them equal to each other. 2x minus x squared equals x squared. 2x equals 2x squared. We know x could equal 0, or, and then I can divide by x, I get 2 equals 2x. Oh, that's, okay. 2 equals 2x, sorry, brain fart, or x equals 1. Oh, and you don't even see me that. That's good. So the two places it intersects are at 0 and x equals 1. So to find the area, I would integrate from 0 to 1. The function on top is the 2x minus x squared. The bottom function is x squared dx. And as I mentioned in class, I just want us to set these up because that's a pretty easy integral to do. And I did integrals at you a lot before. Now, the next thing I want to do is, what about volumes? What if I have that same region and I say I'm going to rotate it around the x-axis? So I'm going to draw it again. Something like that. I have my little generic x. When I rotate this thing about the x-axis, this red line becomes a disc, or a washer, whatever you want to call it. So what I want is the area of the washer. Well, notice for a washer you have an outer circle and an inner circle. So we're going to take the area of the outer circle and subtract the area of the inner circle. Well, we've got a circle, so we have pi big circle squared minus pi raised to the little circle squared. The big circle is, I should probably label that one was 2x squared minus x squared. That was x squared. So the radius is from the x-axis to the top of the line. So for the volume, I will get, we go from 0 to 1, I've got pi. The upper radius is 2x minus x squared, squared for pi r squared, minus the smaller one, pi times x squared, squared dx. So this is effectively saying I'm adding up all the disks from x equals 0 to x equals 1. But mentally I don't try to draw that because I can't draw. I just try to figure out what is the area of that one disk, that generic disk where x can range between 0 and 1. Let's try that one. Same region, y equals x squared, because I'm boring, y equals 2x minus x squared. So there's my region. Now I want to rotate it about the y-axis. So I'm going to do the same thing. I'm going to look at the one slice, my one generic slice between 0 and 1, and see if I rotate this around the y-axis, I'm going to get what they call a shell. To me it looks more like a can. So we get what's called a shell. Now, I want the area of that thing, which is the surface area of a cylinder. So the surface area of a cylinder is 2 pi r h. So the radius is the distance from x to the line you're rotating around. We're rotating around the y-axis, So the distance between x and the y-axis is x. So I'm going to integrate from 0 to 1, 2 pi. My radius here is x, and the height is the length of that line, which is the upper function, 2x minus x squared, minus the bottom function, dx. Now, suppose I didn't want to rotate it around the y-axis. I want to rotate about x equals -2. I'm not having enough room to make this not look horrible. I still have a can. When what you're rotating around, when the axis is parallel to your line, you'll use shell. They call this a shell method. This time, this is my radius. So the radius is this distance, which is x, and it's positive because it's between 0 and 1. And it's this distance, even though this says -2, I know that the distance here is +2. So to find the volume of this, I'm still going to integrate from 0 to 1. I've got 2 pi. Now my radius is x plus 2. And my height is still that 2x minus x squared minus x squared. So that's the disk in the shell method. The key is trying to figure out what the radius is, if it's a shell, and what the height is, and if it's a disk, which one is the outer disk, which one's the inner disk. I'll do another couple of examples in another lecture, but I'm going to end this one now.